All right, welcome back. Let's go to a completely different topic now. So first we talked about bitwise stuff, and now I want to talk about how software gets built, the software development lifecycle. I've stolen a bunch of these slides from Bill Kearney, who is the other wonderful computer science professor here. Encourage you to take a class with him if you can. But yeah, let's get started. Let's talk about how to make software. So here's a silly picture that I found on the internet. It's going to one day make you cry more than it makes you laugh. So this is kind of what happens in the real world when you become a software engineer, or you work your way up in a company to like a management position. You're working on some software in a big team, right? And maybe you're even in charge. And everybody has a different idea in their minds of like what the project is all about, right? Because everything is described in words and documents, and everybody's mental image looks a bit different than everybody else's. And so it's really hard to get your point across in industry, which is unfortunate. But here is a comic kind of making fun of that, and one day you will run into these ideas, all right? If not as a software engineer, in whatever work environment that you end up in, all right? So laugh about it now, but eventually you will cry. I'm sorry. So there's that. And yeah, let's just get started. So let's talk about how to build software. What's going to happen, all right? Somebody's like, maybe you're the boss, you're the CEO of a software company, and they say, all right, here's $1 million. Here's a contract signed by us. I would like you to take a year with your team and build me this software. All right, so that's what happens. What do you do after that? You got the money in your accounts. You've got a bunch of computers and software engineers. How do you do it? So here are the main steps. Here's the traditional steps and the process for making some complicated software. All right, because it's going to take more than a day and more than just a couple CPP files once you get out into the real world, right? And have a bunch of big teams working on stuff. So here's the steps, and here's a picture form of it. And here's the traditional order and the time frame, saying that you have a year. Here's how we're going to split it up. All right, we're going to use 2 months out of that year. That's a sixth of the year, right? To just figure out what needs to happen. We're not even going to write code. We just need to gather requirements. What's going to go on? What does the customer actually want? Go talk to them, interview them, draw pictures. Like what is this software that they're asking you to build? What does it entail? All right, figure out what are called use cases, like all the different ways that the software that you're being asked to write is going to be used by them. And only once you have that information, then can you actually build something, right? You need it first. And so it takes a while to like get them to spit out what they really want. And you have to keep asking questions, okay? So you're going to spend a sixth of the year to just like figure out what they want, all right? And then you're going to spend another 2 months to like design what the code is going to look like, and what all the windows and all the different sections of the program will work as. So that's called the design phase, or the specification generation phase. And so you're going to just write down, still no code, in English, draw pictures. You're going to try to figure out exactly what the code is going to do and how it's all going to work together. So like you're going to like think of all the function names and all the class names, and decide like how they're going to intermingle and fit together, all right, and how they all connect. And so like you have a big document that's planning all that together, because eventually you're going to hand like just a piece off to one of your programmers. So there's a bunch of people working on the same project, and they all need to be up to speed, right? They have to all understand how like their little piece hooks together with everything else. And so you need to spend some time before you write code again, 2 more months, right? Before you even write code, you have to figure out what's going to go on, all right? How all this code is going to work together, all right? And then you're actually ready to write the code, all right? So that's the implementation phase. So like the first one was requirement analysis, then design. Now it's implementation phase time. And like a third of the year is already gone. Yeah, 4 months is already gone. You're only going to spend a quarter of the year to write the code, all right? Only 3 months, because you've already written it all out. Hopefully it should go kind of fast, right? And then hopefully your programmers are following their specifications, all that code, all those ideas that you wrote down. Hopefully they're following along. That may not be the case, right? And so you're going to spend only a quarter of your time to write the code, and you're going to spend just as much time right after that to test it, right? So right after the implementation phase comes the testing phase. You're going to spend the same amount of time testing that code and making sure that it matches the specification. Does that make sense? It's very, very important, all right? Testing is huge in industry. So like you got to make sure like all the functions and the classes are doing what we described them to do, right? And like they're all working together properly. Those are called integration tests. And yeah, just like You're going to give your testers, like that is a legitimate job that you could have as a software engineer. You could be a testing software engineer. Do nothing but testing other people's work, all right? And just making sure that the whole program fits together and works properly, all right? And so you're going to uncover new errors, and you're also going to like send back problems to the developers, and they're going to like keep on incrementally updating things during the testing phase. So you're trying to fix all the bugs and like get the implementation correct. So there's still code writing going on here, but what code you write is dictated by what the testers find. All right, and then finally, this last stage in the picture is called evolution. That comprises these two stages. That's two more months out of the year you have left. You need to give your code to the customer early. All right, the person who's paying you, show them your product in November now, if you started in January. Give it to them, have them try it out, because you know they're going to change their mind. You know they're going to say, oh yeah, I meant this, but I really actually didn't. I said this, but I didn't actually mean that, right? And so you're going to give it to them, and then they're going to tell you what they want changed, all right? And so they might find new bugs and stuff like that. So you'll spend another month like fixing the bugs that they found that you didn't think about, that you couldn't even have imagined how they would figure those things out and get those bugs to appear. And then they're probably going to request new features, like, oh, I wanted this should have been different. And then the cycle starts all over again. This is a cycle for that reason. Does that make sense? It's going to start all over again because that's just how it works, right? They're going to give you new requirements. And then you have to like, all right, let's figure out what they want, design them, implement them, test them, see if that was good enough, and like iterate. Keep on going. Does that make sense? That's the standard way of writing software, all right? And pretty much everybody agrees that like this is a good order, like this is okay. What the people don't agree on, what industry does not agree on, is like the amount of time. Like should this really take a year is kind of the thing to like get it back to the customer. That's what most people disagree about. But yeah, let's now get into programming paradigm. So most people agree with this this setup. But there are some slight disagreements, and I want to talk about all the different ways that people disagree. All right, so the first way is called waterfall. The waterfall programming paradigm is pretty much exactly this, with this amount of time for everything. All right, it's do all those steps in that exact order. It's like water falling off a cliff, right? And it's moving into these different stages, and it can never go back. All right, you can repeat, like you can pump up the water back to the top of the falls, but only after everything is done. All right, so that's waterfall. So you do all those steps in that exact order. And so like here's just another picture of that, like with different pieces involved, like requirement stage, generate the specification and design, and then code it up and then test them. So like this picture is same ideas in just different sections, right? And then it kind of wraps back around, right? So there's pros and cons to all these paradigms. The waterfall design with these kind of stages and the amount of time that they all take, you have to go in that order. Is a nice thing about that is everything is planned out. It's all specified. Certain companies, like they have to use waterfall because maybe they're like getting a government contract and like everything needs to be very highly specified because the software is important. Like you can imagine NASA is going to use waterfall because they want to make sure that everything is designed and ready before they code it up, because that'll give you more guarantees about it being correct. Hopefully, right? And your requirements aren't really going to change. Like the rocket design is already settled at that point. So there's a use case for waterfall, and like everything's planned out, specified. It's useful, right? For like mission critical software like NASA, or for airplane autopilots and stuff like that, like where the design requirements don't really change too much. But there are a lot of cons, and people tend to just not like the waterfall programming paradigm, for a bunch of reasons. You can go look up the Wikipedia page. They think that it's not flexible. Like, all right, if I notice in the implementation phase that there's something wrong with one piece of the design, or like it would have worked better if we like combined these two features into one or something like that, it's too darn late in the implementation phase. You have to implement what was already designed. Does that make sense? Do you see the problem there? So it's not flexible at all. And customers at the same time, right? This picture, just is very, very useful picture to demonstrate that, right? Customers have no clue what they really want, okay? No clue at all. And so, again, for that reason, you may like get new requirements, but you're in the implementation phase now. Sorry, customer, we're not ready to deal with your new requirements yet. Tell me again in 6 months when we wrap back around, right? So that's unfortunate. And then the third thing, kind of what I was saying before, is if all your programmers, they're working on things. They're in the implementation phase and the testing phase. They're noticing like flaws in the design. It was too bad. It was too bad. You have to deal with that design, right? You can't do it a different way. The design phase has already happened. Maybe you can deal with that in the next iteration, in the next loop of all this, okay? So that's waterfall. It does have its pros and cons, okay? There are pros just as much as there are cons. It's useful for mission critical stuff where the requirements aren't really going to change too much, all right? Where people's lives are on the line, like with rocket ships and airplanes and stuff like that. But there are plenty of downsides as well, okay? So here is a competing programming paradigm. It's called the agile programming paradigm. And it's supposed to be fast, right? Agile, fast. And there's different like subtypes of agile, but people tend to agree like this is a better way to write software, assuming you're not writing like autopilots or rocket ships. Most of us are just writing web apps or like iPhone apps and stuff, right? So agile is maybe a better use case for those things. So, okay, agile is a programming paradigm. It uses this same cycle, but it makes it fast. All right, it doesn't take a year to get through this. It takes like a month and a half, 2 months. All right, it works on very small chunks of a program because of that. You can't like finish the whole thing, but you can give little incremental pieces out the door to your client to see if what you were doing was correct or not. All right, so those are, again, your pros and cons. Like pros, the clients can see very quickly like this little iteration of the software after like a month or two to see like if you're doing it right, and they can quickly decide like, oh yeah, actually I told you that, but I didn't mean that, right? So you can go and change things very easily because of that. So that's useful, agile. Cons of agile though is because you're working so fast, it is perceived as more stressful, first of all, because like you have these shorter time frames. So like if you only have a month to do something or 2 months to do something, that seems a lot more stressful than having like a year to do things, I think you can imagine. And so there's like, you feel like it's faster, even though it may not be because you're working on smaller chunks. So there's a psychological factor for sure. And then also because you're like iterating quickly and you're doing a design phase every couple weeks, that means that all of your programmers who like to read Hacker News or go on Reddit and things and find out about all these brand new fancy technologies that they would like to try, they come to you and they're like, I want to use this, please. And that's hard, right? They want to use trendy new stuff, and a lot of the time you just have to tell them no. Because the design phase keeps happening, people can come up with these brand new ideas using these cool new things that they saw on the internet. All right, so that's another thing to worry about. It's a management issue, I guess. But yeah, people tend to agree that Agile is better even with those cons compared to Waterfall for most software projects. All right, so the mantra of Agile is we want to release quickly and release often, get stuff into the hands of the customer so that they can tell us what we're doing right and what we're doing wrong. I just use that feedback to redo that cycle, and the cycle's going quickly. All right, use the feedback that you get to hurry up. All right, and so customers for sure like this. And so your cycle that you're doing all this like design, analysis, implementation, testing, get feedback, all those phases, that cycle is going to not last a year, but like a month or 2 weeks or 6 weeks, something like that. And those cycles are usually called sprints, all right? Like you're sprinting towards a goal where your whole team is working on like a bunch of like little features and like getting it into the software, making sure that it's working, testing it, right? Giving it back to the client to make sure that it's making them happy, right? So all those things happening very quickly in these little sprints that only last a few weeks, okay? So that's Agile in a nutshell. They just disagree about not the order, but the length, okay? So yeah, there have been studies done about Waterfall versus Agile, and so here let's try to see if you can guess something. So Waterfall is all about like we're trying to, or at least the people who want to criticize it, they say that Waterfall is all about attempting to predict the future and like we're designing something but we're not going to implement it for another 6 months, something like that. So you have to be very good about like future-proofing your designs, which may be hard, but sometimes it's not too bad because your design, your implementation doesn't really need to change too much. Like if you got your rocket design is already ready, there's no changes to that. So Waterfall does work, but sometimes you do have to try to predict the future. And then Agile, they say, like again, the people criticizing Waterfall, they're like, all right, Agile is more about responding quickly to the present. See how much better that is? And so let me ask you, like, which do you think, where would you want to work? Pause the video, kind of consider that. That might influence whether you apply to NASA versus you apply to Google or something. So, like, which do you think is more workable? There have been studies done. They are maybe a little biased, but in at least one study, the agile approach is 200 to 300%, 2 to 3 times more likely to result in a successful project versus waterfall. And by success, I mean that the project was delivered to the customer on time and within the budget that was originally agreed upon. All right. That's interesting, right? It's very interesting to think about. But the way that this study was done is they got feedback from people who are like, they've already drunk the agile Kool-Aid. They don't like it. They may be very biased in this approach, but I think it's still a useful metric. All right, maybe there is some truth to it for sure. So here's a diagram from that study. So it was like waterfall project versus agile project. They did a survey and just look at the differences. So red means failed, like the project failed, like it was scrapped, like it did not complete, they did not end up delivering something to the customer. Successful means it like was delivered on time and within budget. And then challenged means that it's still finished, but it was, that's yellow, it was over budget or over time. All right, it took more time than they thought, or it took more money than they thought. And like that's very common. Like you're not really sure what you're getting yourself into and things need to change a lot. So like that's across all the different kinds of projects. It's pretty much the same amount that get challenged. Like you can't predict how much money you need or how much time it's going to take to do something very easily. And so about the same amount for agile versus waterfall for challenged projects. But look at the huge difference between successful projects and failed projects for waterfall versus agile. They give up a lot of failed projects for successful projects. Do you see that? So a lot more things were turned in on time and within budget, and like they weren't scrapped after all. So it's left for you to find out whether or not that means that it was because of like the fast iteration, or maybe like agile projects are just cheaper to begin with. I'm not sure. It really depends. So there is some bias to this study, but it's still a useful metric, I think. Okay. So yeah, that's interesting to think about. And some people disagree on like the best ways to do agile. So there's different subtypes of agile. One very popular one is called Scrum. It's a fun little word. This is a weird one. Scrum is a type of agile. It's pretty popular, and honestly, they've got a lot of different names for the different people that are involved in the Scrum process. It's honestly a lot of role playing that goes on inside of the Scrum Agile framework. And so let me kind of talk to you about it now. So there's plenty of memes about it. The first thing you do is you decide like what it means for your project to be done. What is the definition of done in Scrum? And maybe that's something for you like, all right, it passes all the tests made by the testers, something like that. So like you have to decide for everything that you're promising to give to the client, what does it mean for that piece to be done? So that's useful. I think that applies to many projects. So a lot of people like to steal stuff. Even if you're working on a waterfall project, a lot of people like to steal like stuff from Scrum, like these ideas. All right. Then the next thing you do is you generate what's called a product backlog, which is just a list of things, a list of tasks. It's a to-do list that holds all the things that you need to do before you can give your increment of the project to the customer. All right, including like a list of features, a list of like issues, bug fixes that need to be done, documentation that needs to be written. It's like you just give a big long to-do list, and then you start like giving out those tasks to your programmers. All right, and then you like to usually give like each to-do list task a priority, like how important is it on a scale from 1 to 5, how risky is it, what is it going to involve, how many people is it going to take, and then you give an estimated development time for that feature or that bug fix or whatever. And that is just an estimate. It is very hard to come up with estimates for like how long it will take to do something, because you don't really know until you get started, and so that estimate might update, but it's just a first guess at that. And yeah, there's a lot of role playing going on in Scrum. So there's somebody that's called a product owner. That's either like the client themselves or somebody pretending to be the client, and like they're coming up with the backlog and the priorities, and hopefully you're working with the client on that list. All right. So yeah, there's somebody in charge there. They're called the product owner, and yeah, there's more role playing to go along with it. There's somebody called the Scrum Master, which is hilarious, and they're kind of like project managers, I guess. and they guide the Scrum process. All right, I hate the word process. That's why I work in academia, not industry. I hate these terms, but I have to tell them to you today. All right, they guide the process, and they just make sure that like everybody is understanding what's being done. They're on board. They try to like they're the ones in the meetings rather than the developers, which is nice. And so yeah, what happens in Scrum is like the sprints like to be very small. Like they're just a month long. They're just 2 weeks long. They're the ones who came up with the word sprint, by the way. So at the start of their like maybe it's a 2-week sprint to get something out the door. They have one like longer meeting, like a planning event, where they take a bunch of tasks from the top of their product backlog, right? And that creates a smaller backlog for just the sprint. That's the list of tasks I want to complete for just this sprint. So you've got a main product backlog. That's a big to-do list for all of like the software. I need to complete all of these to complete the software. Maybe it'll take a year or something. Doesn't matter. So it's a big long to-do list with all those priorities, right? So you've got like this one was priority 5. This one was priority 3, priority 2. And then what you do is you're, for every sprint, every 2 weeks or something, in your planning session, you're going to take off the top of that list maybe the most important things, the things that are high priority, and you're going to take them and put them on your sprint backlog. And then those are the ones you're going to focus on for this sprint. And you're going to hand off those tasks to your developers and teams. And yeah, and then like the hope is that like they get crossed off by the end of this process, by the end of the sprint. All right, and so they really like timing things. Like the planning event is no longer than 4 hours because everybody wants to go do their real work, which is nice. So they're really good about time boxing, which is the word they like to use. So the team, every day you're working on stuff. All of your developers are working out of the sprint backlog. They like to do little 15-minute daily stand-up meetings, and they legitimately stand up because they all don't want to be in there anyway. They want to get out as soon as possible, so they stand up. They don't use chairs. They just talk about like what they're working on. So at each meeting, like it's called the daily scrum. Each member of the group that's working on something out of the sprint backlog is like they're talking about what they did the day before, like what they're going to do today, and like anything that's in their way and anything they need to discuss. They'll like set up little mini meetings with each other to get over any roadblocks, which is super nice, right? They make sure that the meetings are 15 minutes and they don't sit down because of that. They know that they all want to get out the door. So that's super nice, I think, and useful. And yeah, it's a good way to just collaborate and get ready and then go off and do the work you care about doing. All right, so they kind of try to keep the meetings to a minimum in Scrum, which is nice. And this idea of stand-up meetings and accountability and making sure everybody's on the same page is huge. Like everywhere, every internship that I ever did, even if they didn't use Scrum to do their software development, they did this. All right, they did a Scrum-style daily meeting that like everybody was just going around the room talking about what they were doing because it's a super useful thing. I hope you can imagine. So even if you're not doing Scrum, you will almost certainly be doing this once you get to industry. All right, these daily meetings, stand-up meetings that are super fast are very, very helpful. All right, it's helpful for the boss as well to see what everybody's working on and struggling with and give guidance. So yeah, what happens like throughout the sprint is like everybody on the team is working through the backlog, trying to like cross things off the list, and hopefully by the end of your sprint, you're done with everything. All right, so here's a picture form of that. Like apparently this example is a 30-day sprint, but it doesn't really matter. So like you've got your main product backlog. You take off pieces of that, just little shavings of what you need to do, what you think you can do in the next sprint phase. And then you work on that every 30 days. Like your sprint is 30 days, you try to get through the sprint backlog, essentially. All right, and then like every day you just like keep on monitoring your progress. You have little stand-up meetings that are very short. And in theory, you've crossed everything off your sprint backlog by the end of the sprint, and you have a little piece of the software to give to the customer and say, like, here's what we did. Do you like it or not? All right, and that's very useful for the customers. So yeah, at the end of your cycle, whether it's 2 weeks, a month, 6 weeks, doesn't matter. At the end of your sprint, they do have one last meeting, like a 2-hour meeting. They do like to keep them short if they can, where like everybody goes through and they make sure like everything worked out properly. All right, They see like, did we cross everything off the list? What went wrong? What can we change for next time? What went right? How can we improve the process? I hate that word so much. How can we improve it for next time, for next sprint? And then it's like they make sure that everything's polished and ready to give to the customer. So yeah, that's Scrum in a nutshell. And you can see, like I said, exact amounts of time for all these things. Like they really like to time limit themselves. They like to time box things. That's another word for that. To make sure that nobody's stuck in meetings all day long. All right. So Scrum is useful, has a bunch of weird words, and people like to take pieces of it, especially these stand-up meetings, even if they're not using actual Scrum. They're doing some other type of Agile, or even if they're doing Waterfall. Okay. So yeah, here's one more picture about Scrum. Because you have all these things, you've made all these lists, you got all these things that you've written down, and you're like checking them off. It's really easy to make data and see, like, for everybody, print this out every day to see how people are doing, and see how things are going. So here's an example of a burn down chart. It's where you get to see like how all the tasks are being completed. So they're reusing this axis, which is kind of weird. It's like each task has a estimated amount of time it's going to take. And so like that starts out like you have a bunch of time that it's going to take to do all your stuff at the start of a sprint. And then also every task has like a number, right? You have a bunch of tasks that you need to complete. So at the very start, you have a bunch of tasks and it's going to take a lot of time. And then the goal is to work your way down to 0 tasks left and 0 remaining time left to complete those tasks. So like ideally, your burn down would look like this. But like here's a graph of like remaining tasks. Sometimes they stay steady because you're just continuing to work on something. It takes a couple days to get it done. But eventually, like, tasks get checked off, and then also the amount of time to do things. Like, maybe you notice, like, it's going to take even more time than you thought, so, like, it can go up. But in theory, eventually it goes down to 0. Like, there's no time needed to do everything. Everything is done. And so, like, as tasks get completed, maybe it takes a couple days to do those things, but eventually, you work your way down, and there's no time. Like, the time gets down to 0 as well. Right, so that's a useful chart for managers to see, right? To see if everybody's doing the right stuff. Yeah. So that's an example of something that people like to see, and like you can see your progress as well there too. All right. So throughout the sprint, hopefully everybody's trying hard to get it down to 0 on both axes. So yeah, that's Scrum in a nutshell. It's a type of Agile. So we've learned about Agile, which is fast version of Waterfall. All right, so that's me using all the terms that you've learned. There's one more kind of programming paradigm that's kind of out in left field that is becoming more and more popular, and it's honestly something that we do a lot in class already. And so there are plenty of very popular companies that are doing this thing called TDD. It's short for test-driven development, and it's where tests are very important. They're even more important than they already were. Right? You're already in all these other paradigms. You're spending time. The same amount of time testing after you've implemented, but TDD takes it one step further than that. All right, and so I'm a proponent of TDD. I like it a lot, so I want to teach you about it. So here it is. Test-driven development is one of the few programming paradigms that disagrees not about the amount of time that this cycle takes, but the order. What they do is they have swapped the implementation and the testing phases. They say write the tests first before you even write code. All right, and we've done that a little bit in class, I think. I've honestly, like every one of your labs, that's true, isn't it? So you've been forced to do TDD, and I think you have maybe found that it's helpful, right? By giving you tests up front, you kind of know what's expected. Does that make sense? And that's very useful in industry as well. So they swap the testing phase and the coding phase, and so they like to write the tests before they get into code. And so I think you can see like that's useful. That's useful for you in your labs, right? Because you get to see like how things are going to be used. You get to try them out. Like pretend I have these functions. How are they actually going to be used? Let me write tests to confirm that like my intuition is correct. And that's going to guide you as you write your real code, as you actually implement that class or that function or whatever. Okay? So that's very important and very useful, I think. So their mantra is red, green, refactor. Because like right at the start, like all the tests fail because you haven't written anything. So all the tests are red at the beginning. But the more you implement, the more the tests, they turn green. All right. And then usually the first time you write something, or you're just trying to get the test to pass, the code doesn't look very pretty. So after that, you like to refactor your code, make it prettier, give documentation, clean it up. That's what refactoring means. Just cleaning it up, making it better, because you'll have more context at that point. Like you're done with everything, you see how it fits together better, and then you can clean up the code because of that. So I think that this is a very good programming paradigm, and it's worth using. So when you get into industry, try to convince people to start doing it this way. So yeah, it's after that, like it's time for the next feature, and you write the test cases first. And then you go and implement, get the test cases to pass. So it's always a cycle of red-green refactor for the TDD people. Tests fail, you get them to pass. You write the tests, they all fail because you haven't done anything. Get them to pass, and then clean up your code once you like understand how everything fits together better now that you've implemented it. Okay? So yeah, that's pretty nice, I think. There's plenty of pros and cons, of course, to all of this stuff. But let's talk about them for TDD. All right, so the pros of TDD. If you have a good test suite, that's just like that's what it means to have like all of your tests together. You put them in a test suite, we say. Then you can be pretty confident that like when you implement, you can be pretty confident like because you had a good test suite and all your tests were passing, you can be pretty confident that whenever you write new things, you have not broken the old things because those old tests are still running every time you like submit your new code changes. All right, which is nice. And then also because of that, like if you break something, like you know the version of the code where all the tests pass, and you can go back to them. Everybody uses like Git, for example. They like to use version control systems, and just you can go back to the version where the tests passed. That's true of all your paradigms. People like to version control their code, so that's something to look into. So those are like that just means you can be brave, and that's nice. And then cons of TDD, there are cons too. Because you're writing a lot of tests and you're giving a lot of weight to tests, it may take a long time to run all of the tests that you have written and all the programmers in the team have written too. Because you want to make sure everything is still passing, right, when you make changes. So you might just have to like run them forever. This is called like continuous testing. So you might have to like run them at night or just like keep them running for the end of time. And you might not know for a couple hours whether or not you broke something. So that's an issue, potentially. But you can usually solve that issue with more processing power, right? So just buy another server to like run more tests in parallel. Another con that is kind of inherent, or like, what's the right word? Just kind of baked into the idea of TDD is a lot of the time, like your teams are small, and so you may not have a dedicated test writer. So a lot of the time, the same programmer that's making this feature is the one who's writing the tests for it before they implement it. And so if it's the same person, they might have the same blind spot, right? The code that they write might share the same blind spot as the test. They might have forgotten to implement something and therefore have forgotten to write a test about that thing. All right, so it may be useful to like split up who writes the tests versus who implements the code to pass the tests. That's useful a lot of the time. And so that is solvable, but it is a con to worry about. And then, yeah, also, when you get new requirements from your customer, like you need new things, or just like you realize that like we can rewrite the code, we can refactor it in this way. When those things change, when the code structure changes or the requirements change, you have to rewrite the tests that like use the old structure. All right, and that might take some time because you've written a lot of tests. That is useful, and I think it's worth it, but it is something to worry about. It's going to take some time and cost money. And then finally, there are some things that you just can't test. Like, you can't test things like that are experiences, like a video game. You just have to have somebody go and like play the game, right? Or a graphical user interface. You can't test that it's like easy to use. You have to just like go give it to old retired people and make sure that they can understand it. Like you have to like do that. And I guess you can count that as a test, but it takes more effort, right, to get all that stuff. So yeah, that's TDD, pros and cons. We might as well write code at least once today. So here, let's have an example of test-driven development. Let's make some code that practices these bitwise operators that we learned about. So and or and not and all those fun things. So let's do a TDD example of that. And let's say that we're going to write, here's what's on our backlog, set third bit and is third bit set. Those are the two functions I'd like to write. All right. So those are two functions that I want to deal with. And what their job is they're going to like take a number and see if the third bit of it is set or not. So like, remember what the third bit is. So like here's 0, 1, 2, 3. This is a number with the third bit set, and like 0, 0, 1, 1. That's a number without the third bit set. Okay, so we want a function to check if those bits are set, and then also a function to set the third bit of any number, regardless of whether it's set already. So like make sure it's set by the end of the function call. So that then you'll like pass a number by reference or something. And so like if it's this, 0, 1, 0, 1, I guess. So here's like bit 0, bit 1, bit 2, bit 3. So like go in and set that bit to a 1. That's the meaning of all these functions. Does that make sense? So that's what we would like to do. And so let's start out our functions as just stubs that return a dummy answer or that do nothing, whatever we need to compile. And then we'll write tests. All the tests are going to fail because the function is not doing anything right now. And then, yeah, we'll make it work. So this is the test-driven development process. Let's do, I'll call it TDD example. And honestly, we've pretty much been doing this in class. Definitely in your lectures, but I've also, you've heard me say like, all right, let's pretend we have this already. Let's see how we use it first, and then we'll go write it. That's TDD, right? That's TDD working. It's useful. So, okay, I got these functions that I want, right? I want to call it set third bit and is third bit set. What are they going to look like? Let's just give their declarations. All right, so set third bit is going to take a number by reference, right? Because we want to set the third bit of it, so it'll be void. And then is third bit set will take a number, it doesn't have to be by reference this time, and it's bool, right? It'll say true if the third bit is set, false if it's not. All right, so that's what I want here. And now let's make some tests. All right, or we can make some stubs as well, but we also want to make some tests. Let's see. Yeah, let's do the stubs first, maybe. So here are my stubs. So the first one, a void function, doesn't have to return anything, doesn't have to do anything at all. So a stub is just like, I'm going to do nothing right now. And then is third bit set, needs to return a bool. Let's cheat, and we'll just say, all right, return true. Third bit is always set of every number. So these are stubs. These are obviously incorrect, but they will compile, yeah? And now we're ready to write tests. Now we are ready to write our tests. Let's make a test for set third bit and a test for is third bit set. I'm going to need the assert true function. So we got stubs right now. Let's make some functions that involve assert true. Looks like I can get one in lecture 15 main. There it is. All right, give me that one. So there's my assert true. I need the string library to use it. And now we are ready to write our tests. So I'll make one called test is third bit set, and then another for test set third bit. All right, and so those are going to hold my tests, and then I'll run them in main. So here in main, I'll actually run the tests. Test is third bit. What's the order? Test set third bit first, and then test is third bit set. There. So yeah, that's my program. And so right now I've got stubs for those two functions, and now let's write tests to see if they're going to pass or not. All right. So here are my stubs and my assert true. I'm going to use that to write some tests right now. So test set third bit. So what are some examples? So this is a number, right? Here's a number with the third bit set already. What is that? That's 8, 9, 10, 11. That's 11 in decimal. And then this one is 3, right? This one is 3 in decimal. That's a good example number without the third bit set. Okay, so let's use those. So like if we call set third bit on 11, it shouldn't change, right? Because like it's just replacing a 1 with a 1. It's already there. So it should remain 11. And then if we call set third bit on the 3, it should change it to a 1 and make it 11. Does that make sense? So those are some good tests. Let's make that. So, okay. Yeah, I guess I'm going to need a variable. So int x equals 3. So let's start it at 3, right? So that's this one. And then if I call set third bit on it, it should turn it into 11, right? Put a 1 there. So set third bit on x. Take it by reference, mess with it. Now it should be the case that x has been changed to 11. So assert true, that's what I assert. Assert true that x is equal to 11 now. Yeah? And so what's the name of this test? What do we want to call it? Call it set third bit on 3. Okay, I hope that makes sense. That is a good test. And then we can make another one for like if it's already 11, setting the bit 3, it's already set. It should stay 11. Let's do that test. So let's reuse x here. So x is 11. Calling set third bit now should keep it 11. See that? Shouldn't like move it back to 3 or something. Shouldn't toggle the bit. And that has a new name. So that's a good test. Does that make sense? I hope you see it. So that's a good one. And then let's make another one for this one. Test is third bit set. So like we have again 2 examples. This one should give back true for 11 because the third bit is set, and for 3 it should give back false because it isn't set. Okay, so assert true that is third bit set on 11 gives back true, right? Because that's what it should do because it is set for 11. So that's what it should do, and a name for this. I'm running out of room. We'll call this is third bit set on 11. All right, so there's my test. I hope you see it working. And then the same for the 3, right? Is third bit set for 3 should give back false. Yes? Because it's not set. That bit position is set to a 0. All right, and I know I'm a broken record. I've said this before, but maybe you haven't seen this in the context of assert true. I can simplify these tests. I can simplify these conditions because like this equals true and equals false, they're kind of redundant, especially the first one, right? Remember me saying that? So there's a better way. Instead of those, I'm going to change them. These two are about to be equivalent to the above. These are equivalent to the above. So instead of these, remember that assert true is just making sure that its condition is true. I just want to make sure that is third bit set 11 gives back true, and that will this will get replaced with true if that is true, right? And so this equals true is redundant, right? I just want this first part to assert true to be true. So is third bit set, it should give back true. I'm wanting it to give back true. Do you see that? That's all that I care about. So I can just say assert true that is third bit set of 11 returns true to me. Does that make sense? It is a little weird to think about this, but hopefully I've explained it enough by now. Please yell at me in office hours if you have any questions about that, but this is the same, right? It's the same as checking if it's equal to true. There is no difference. Just like it will give back true if it returns true, right? That's the same thing. It's going to return true, and we're just asserting that that result is true, all right? And same with this. I want to assert that is third bit set of 3 is false. Another way of saying that is saying that I want to assert that the negation of his third bit set is true. Does that make sense? Just like make sure that like this gives back false so that when I negate it, it gives back true. So it's cleaner and easier to read, honestly, once you get used to it. It's like, all right, I want to assert that, all right, the third bit is set of 11 and the third bit of 3 is not set. See how I'm reading that? Just like you'll eventually like get up to speed and understand like, okay, that just means that I want this to have returned false. Because I'm negating it, I want the negation to give back true. Right? Just like this one, I want it to give back true because I'm not doing anything. I'm just like using its result. I want it to give back true because that's what I'm asserting. Okay? I hope that made enough sense. It is hard to explain in words, but hopefully you can kind of see it a little bit. Okay? So yeah, those are my tests. I've got them. I've made them, and I'm running them here in main. Am I in the wrong file? Did I not save it? Oh, okay, yeah. Dash out 2D example. And it looks like we have some of them passing. Our stubs kind of passed for some of them, which makes sense. Like setting the third bit of 3, like what is our current function doing for set third bit? It's doing nothing at all, right? Doing nothing at all. And that's not good enough for 3, but it is good enough for 11. So like it should have stayed the same. So like it's just passing even though it's wrong. And then same for is third bit set of 11. We've just like hard coded like, oh yeah, it's always going to return true. And so it's like, yeah, third bit's always set. So it'll pass for 11, but of course fail for 3 because the third bit isn't really set. So now we've got some red, right? Some red, we want to make them green. Okay, that's our goal. And then potentially refactor if we see that we can improve anything. So, okay, let's actually give some implementations here. Let's do set third bit, and then is third bit set. So they're both going to involve the same special number if you think about it. So let's see here. Let's do is third bit set. Do you remember how to check if the third bit is set, like of 11? How do we know that it was set? Like you got your number, it's going to be an and, right? It's going to be an and operation with a number with just that bit set. So what is that? That's 8, but there's an easy way to get it, right? And it's going to force a 0 everywhere, but potentially right here. Because if this number was a 0, it would have been a 0, but because it's a 1, it'll be a 1. You see that? And that's how we know. That's how we know if it was set or not. And a special number with just that bit set. And so like if it wasn't set, dashed, if it was just a 0, then it would have given a 0 here because it would have been false and the whole answer would have been 0. Remember it now? Like that. That's what we look at. Just like was it 0 or not 0? And then same for setting the bit. You just set, you OR, right? To set a bit, you OR with the number with just that bit set. That one. Does that make sense? And so a very quick way of getting a number with the third bit set is to use our shifts. Okay? Is to use our shifts. And so here, let's do them now. So to set the third bit, you're going to take your number, and then you're going to OR it with a number with the third bit set, which is, let's just hard code it for now. That's 8. Okay? It is the number 8. Maybe you said X ORed with 8. It's kind of hard to understand though, but it's gonna work. That is the 1 0 0 0. Oops. All right, so that's 8. That'll work. And then is third bit set, just like return whether or not taking your number, anding it with the number with the third bit set, 1 0 0 0, which is 8 again, making sure that that is not equal to 0. Does that make sense? It's like if it's 0, that means it wasn't set, because it was all zeros at the end. But if it was, like if it gave you back 8, something non-zero, then it was set. Okay, so that's that, and that should get them to pass. Cool. And so like we got green, and now we want to refactor. All right, so this hard-coded 8, it's hard to understand. Like, oh yeah, why is that setting the third bit? It's cleaner, and maybe you'll discover that like once you come back, look again with a fresh set of eyes. Like, okay, how do I get a number with the third bit set? And it's easy to explain to other people. I just do that. Does that make sense? This is easily a way to like start with a number with the 0th bit set, shift it over so that the third bit is set. All right, we'll do the same for this one. And now people who look at your code, who are reviewing it and testing it, can easily see like, oh yeah, I'm anding with a number with the third bit set, I'm ORing with a number with the third bit set. I can understand why that's working. It's much better than hard coding the 8, right? So there's my refactor stage. Does that make sense? And then maybe if you had these first, you would refactor even the tests. Up to you. So yeah, now they're passing. We got green, we refactored, and I think that's a very good way of writing programs. Test-driven development. All right. So encourage you to use it if you can. And yeah, that's pretty much what I have for the day's lecture. What I would do if this were like in class, I would ask you all to like get into groups with people sitting next to you and have a little daily scrum. So I think it would be useful for you to pause the video and like take out a stuffed animal or something, or like go to a sibling or a parent and like talk out these things, because it really does help. Or come to office hours, talk to me, give me your daily scrum. All right, let's have a stand-up meeting. Come and talk to me about it. We can have our own stand-up meeting together, or go to the tutorial center. I honestly think it is useful to get in the habit of doing this. This is honestly another reason why I ask you for check-in surveys. It's kind of like a stand-up meeting, isn't it? So yeah, do your best. Go talk to your favorite stuffed animal or something, and like go talk about like what you're working on, what you're struggling with, and like what you plan to do today or tomorrow regarding those two things for like the next lab in this class or something. Okay, or whatever is iBooks assignment you're working on. So yeah, it doesn't have to be long. It's a stand-up meeting. You gotta stand up while you're doing it. And I think that's all that I have to say. It is useful. I encourage you to try it. And with that, we have completed this set of slides about two kind of completely different ideas, but I tied them back together. Tied them back together at the end there. So I did my best. All right. So I think that's all that I've got. Do ask me any questions that you have, as usual, and I will see you later.